everyone. I'm Sujani, faculty in physics at Institute of Aeronautical Engineering, Hyderabad. Today we are going to discuss definitions and terminology involved with module 5, that is harmonic oscillations and waves in one dimension. Before going into the details of the definitions, let us first look at what is a definition and why is it important to define terms correctly. What is a definition? The act of defining or making something definite, distinct and clear. Then we call it a definition. Or the formal statement of the meaning or the significance of a word or a phrase, idiom, etc. as we see it in dictionaries. Or a statement is something that expresses the essential nature of something. This is how we are going to define. Now, why is definition so important? Why is it so important? Because definitions enable us to have a common understanding of the word or the subject. They allow us, all of us, to be on the same page when we are discussing about a topic which is in common. Also, we have to make sure that the words and phrases that we use are definite and everyone will understand them. Now coming to terminology. What is terminology? It is the body of terms that are used with a particular technical application in a subject of study or a profession. And what is the importance of terminology? So whenever we are defining a subject, we are using particular terms. What role does this terminology play? It plays a very important role in understanding the context and the specialized text. Understanding the intricate terminological details of the technical and scientific context helps students to comprehend what the main essence of the document is. Not only that, it also helps specialists to transmit the content in a very effective manner. That is why we need to understand what are definitions and terminology. So you need to take care whenever you are writing a definition, the very meaning or the essence of it should remain as it is. And the particular terms that are involved with that particular subject have to be used. Now coming to the module 5, we are going to discuss all the definitions and terminologies that are involved in module 5. So what is the brief outline of the module? We are going to discuss about simple harmonic oscillators, damped harmonic oscillators, forced harmonic oscillators. So all these three are related to oscillation. So we are going to discuss all definitions and terms that are involved with the different types of oscillators. And also we are going to see the definitions and terms related to transverse and longitudinal waves, then reflection and transmission of waves at boundary, and harmonics of waves. All these three are related to waves. So we are going to discuss the definitions and terminology one by one. So the first one, what do you understand by periodic motion? What is periodic motion? A wave in which a uniform series of crests and troughs follow one another in regular succession. So when I say periodic motion, a periodic motion means it repeats itself at regular intervals of time. So when we are talking about a wave here, it will have a series of crests and troughs that follow one another in a regular succession. So now if you see in our day-to-day life, we come across many types of periodic motion. No? So the swing we see is a periodic motion. So when we are talking about the waves on a stretched string, so in contrast, the waves on a stretched string, they need not follow regular repeated patterns. So when they are not regular and repeated patterns, we do not call it periodic. Only when they are regular and repeat itself after regular intervals of time, we call them as periodic motion. Let us see the example. So here if you see, we said in a periodic motion, the crests and troughs follow one another. So if I see in this particular wave motion, which is plotted for time versus displacement. This is the displacement along the y-axis and the time along the x-axis. So we have a series of crests and trough. This is the crest and this is a trough. So with time, what is happening? The crest and trough are repeating after regular intervals of time. See, in a period T, we have one wave, and in the second period also, we have a similar wave. So this is also a crest and this is also a trough. So this is what we are talking about. A series of crests and troughs follow one another in regular succession. Next, define simple harmonic motion. In short form, we may also call it as SHM, simple harmonic motion. It is a special type of periodic motion in which the restoring force on the moving object is directly proportional to the object's displacement, which is in magnitude, and acts towards the object's equilibrium position. So, two things we need to understand. The restoring force is directly proportional to the displacement. That is the first thing. And the second thing, it acts towards the equilibrium position. So this is the second thing. So in simple harmonic motion. So let us try to understand this definition with the help of this diagram. Now we are considering a block of mass M, which is attached to a spring. So we have taken a spring, one end of the spring we are attaching a mass and the other one is connected to a rigid support. This is a fixed support. So now initially the mass is at this position. I will call this position as the equilibrium position. Now when we apply a force and just displace this mass, means I will bring it till here. This is the position. I am just displacing it from the equilibrium position. From the equilibrium position, we have moved it here and left. Now, this mass will come back to its equilibrium position. So, there is a force that acts in the opposite direction and this is proportional to the displacement. The more we displace it, the more the force. And you see in the next case, we have pushed it towards the rigid support. Now the force acts in the opposite direction, again trying to bring it back to the equilibrium. So from here it is coming here, equilibrium position. From here it is coming to the equilibrium. And in both the cases, if you see, more the displacement, more the force. So here this is the displacement and in this case this is the displacement. So both the things we need to understand. Force directly proportional to the displacement and it is always directed towards the equilibrium position. Now the third one, define displacement of a particle in simple harmonic motion. So if a particle is executing simple harmonic motion, how do we measure its displacement? So the distance traveled by the vibrating particle at any instant of time, what point of time we want to know the displacement. So how do we measure it? The distance traveled by the vibrating particle from its mean position. We call it as displacement. So let us understand it with the help of this diagram. So here again we have plotted a graph for displacement versus time. Time taken along the x-axis and displacement along the y-axis, means as the time lapses, the particle is getting displaced. How it is displaced, that is what we are going to understand. Now if you see, at 0.5 seconds the particle is here. So I can say the displacement of the particle at 0.5 seconds is 2 centimeters. If I am taking along the y-axis displacement in centimeters. Now at 2.5 seconds, What is the displacement? The displacement is 4 centimeters. So at any point of time, I can find the displacement at 3 seconds. So at 3 seconds, the particle is here. So how are we measuring this displacement? Always with respect to the mean. I take this as the equilibrium position. So suppose I want to find the displacement at 4.5 seconds at this point. So now what is the displacement here? Is this? Again, we are measuring it in the downward direction with respect to the equilibrium position. So this is the displacement. So the distance traveled by the particle at any instant of time from the mean position. So here we have taken this as the reference point or the mean position. So we are measuring the displacement with respect to this. So if I see here, it will be this. So that is how we measure the displacement. Now define amplitude. What is amplitude? The maximum displacement of the particle from the mean position. At any point of time, we can measure its displacement, but wherever there is maximum displacement, we will call it as amplitude. Now you see in the figure, we have marked it by red. So here the displacement is maximum. So we call it as amplitude. At all other points, I'll call this as displacement, this as displacement, this as displacement. But wherever it is maximum, we are calling it as amplitude. Amplitude maximum in the upward direction. Here amplitude maximum, displacement in the downward direction. Both are called amplitude. And it is usually denoted by capital A. Now define frequency of a body. What is frequency? The number of oscillations per second. We define it as frequency. Frequency is defined as the number of oscillations made per second, and the formula is 1 upon T, where T here is the time period. Time taken for one complete oscillation. We call it as time period. So 1 upon T, the time period, gives us the frequency. And if you have to calculate the angular frequency omega, omega is 2 pi f, or we can also write it as 2 pi upon T. So frequency is 1 upon T and angular frequency is 2 pi upon T. Next, define phase of a vibrating body. What is a phase? Phase of a vibrating particle at any instant is the state of vibration of the oscillating particle regarding its displacement and direction of vibration at that particular instant. So when we are talking about phase, the phase talks about the state of vibration. Also, it takes into consideration the displacement as well as the direction of vibration. And how do we express it? So if you see the expression for the position of a particle as a function of time, because the displacement varies with time. So x is equal to a sine omega t plus phi. And at time t is equal to 0. Then what happens? At time t is equal to 0, we will call it as the initial phase, because omega t plus phi is the phase of the particle. And when t is equal to 0, we are left with phase. So the phase angle at time t is equal to 0, we will call it as the initial phase. Now, once you know phase, what is phase difference? Because we have discussed in detail about this regarding the waves, superposition of waves. So, how do we understand this? So, the phase difference is the difference of total phase angles of two particles executing simple harmonic motion with respect to the mean position, that is known as the phase difference. So when you are talking about two particles which are in simple harmonic motion, you will consider the phase of both the particles, and the difference in the total phase angles, we call it as the phase difference. Now, two particles are said to be in the same phase when the phase difference between them is an even multiple of pi. So this is the condition. So when they are in the same phase, when do you say they are in the same phase? Now let us see the phase difference. Define phase difference between two simple harmonic motions. So the difference of the total phase angles of two particles executing simple harmonic motion. So when we are considering two particles that are in simple harmonic motion, how do we calculate the phase difference? So two particles are said to be in the same phase when the phase difference is an integral or even multiple of pi. So here delta phi, that is here delta phi denotes the phase difference, is given by n pi, where n takes on the value 0, 2, 4, 6. So we have pi, 2 pi, 4 pi, 6 pi. For all these values, the particles will be in the same phase. Now, two vibrating particles are in opposite phase when the difference between them is an odd multiple of pi. So, if you consider the delta phi is equal to 2n plus 1 into pi. So, for n taking all the values, n is equal to 0, 1, 2, 3 and so on. So, if you substitute n is equal to 0, we have pi. For n is equal to 1, we have 3 pi. For n is equal to 2, we have 5 pi. So, for all these values, they are opposite in phase. So, the conditions we are arriving at, if the phase difference is an even multiple of pi, they are in the same phase. And if the phase difference is an odd multiple of pi, they are in opposite phase. Define the term epoch. What is this epoch? Epoch refers to the displacement acquired by an oscillating body when the time t is equal to 0. Means at the initial position, we call it as epoch. Or I can also say it is the initial phase. It is thus measured in standard length units of meters or centimeters. In SI unit, we measure it in meter, or in CGS it is expressed in centimeter. Now define natural frequency of a vibrating body. What is the natural frequency? Free vibrations of an elastic body are called natural vibrations and occur at a frequency called the natural frequency. So what are these free vibrations? Suppose if you take an object, we will consider the case of a simple pendulum, a small bob attached to a string which is tied to a rigid support. Suppose I displace this bob from here, I bring it here and leave it. Then what happens? The bob will start oscillating with its own frequency. I am not applying any force. We have just displaced it. So the object or the bob will start vibrating with its own natural frequency. We call them as natural vibrations or free vibrations. Now define damped oscillation. What is a damped oscillation? Damping is the resistance offered to the oscillation. So whenever we are considering an oscillation, so the same thing we will consider again, the simple pendulum. When this pendulum is oscillating like this, there are some resistive forces that are acting on this object. So the damping is the resistance offered to the oscillation. It may be due to air, or if we keep suspended in an oil bath. Suppose I keep the bob immersed in oil. There will be some resistance offered for the movement of this object. So that we call it as damping. So because of damping, what happens? The oscillation fades with time and you will call it as damped oscillation. Means the amplitude goes on decreasing. So due to damping, the amplitude of the oscillation reduces with time. Means if the oscillation is like this, so gradually the oscillations, the amplitude will go on decrease. So the reduction in amplitude is a result of energy loss. So why is the amplitude reducing? Because there is loss of energy from the system in overcoming the external forces. So whatever damping forces are there, like friction or air resistance, So the system has to overcome these forces. So because of that, there will be energy loss. And due to that, the amplitude goes on decreasing. Such oscillations, we call them as damped oscillations. Now, when can we call an oscillator lightly damped? So when we are talking about damping oscillations, we discuss three cases. One is underdamped or light damped, underdamping. The second one will be critical damping, and the third one will be overdamping. So we will understand all the three. So first we are talking about lightly damped. When do you say it is lightly damped? When the oscillation, when the object reaches the equilibrium point faster, but oscillations across the equilibrium point continue one or more time. And in underdamped oscillations, the damping constant is less than 1. So what happens here in underdamping? The object or the oscillation will not come to rest immediately. It will oscillate and then slowly come to rest. So the damping constant is always less than 1. So the oscillation becomes stable very slowly and have the least energy dissipation. The energy that is lost is very minimum. Then we call it as light damping. Now, when do we say that it is critically damped? When can we call an oscillator to be critically damped? So, in critical damping, the oscillation or the object returns to its equilibrium point fast and does not create any oscillations. It does not oscillate at all about the mean position. It will just come to rest. Okay. So, in critical damping, the damping applied is such that the force available is just sufficient to bring the oscillation to equilibrium without any further back and forth movement. So the oscillation in critical damping, it just comes to the equilibrium position. It comes to rest without any oscillation. Now, when do we say it is heavily damped or overdamped? So the damping in which the oscillation reaches the equilibrium point slowly and do not create any oscillations. So even in case of critical, there are no oscillations. In heavy damped also, there are no oscillations. We find oscillations only in case of light damping. But the difference here is in critical damping, it comes to equilibrium fast. But in heavy damping, it comes to rest very slowly. So then we call them as overdamped oscillations. In overdamped oscillation, the damping applied is more than the required value of damping in order to bring the oscillations to rest, because the damping applied is more than the required value which we have to apply to bring it to rest. So we have overdamping. So what are the two forces that act in damped vibrations? What are the forces that are acting on the object in case of damped oscillations? So there are two forces that act. So one is the frictional force and the other is the restoring force. So if we are talking about a simple harmonic motion, we have seen that it is the restoring force that tries to bring it back to the normal position. But in case of damping, we have another force which we call as the frictional force that acts on the object. So there are two forces that are acting here. One is the restoring force and the other is the frictional force. Next, define forced vibrations. What are forced vibrations? So when a body oscillates by being influenced by an external periodic force, when there is an external periodic force that is acting on the system, so then we call it as forced oscillation. Periodic means we are applying the force periodically. So then we call it as external periodic force. So what happens here? The amplitude of oscillation experiences damping, but it remains constant. So what is happening? Even though there is damping, because of the continuous application of external force, what is happening? There is continuous supply of energy to the system. So it sustains the oscillation. So in case of forced vibrations. So what are the three forces acting upon a particle in forced oscillator? So in damping we have seen two forces, the frictional force and the force, the restoring force that tries to bring it back to the equilibrium position. In case of a forced oscillator, there are three forces. So what are the three forces? The first one is the restoring force, which tries to bring it back to the equilibrium position. Then the frictional forces, which tries to oppose the movement of the object. And then we have the external applied force, external applied periodic force, which we are applying to sustain the oscillation. So there are three forces here, the restoring force, the frictional force, and the external periodic force. Define resonance. What is resonance? Oscillation of an object with maximum amplitude. So in resonance, the amplitude of oscillation is maximum. So when the frequency of the applied force equals to the natural frequency, then we see a phenomena which is called as resonance. So now we have already discussed both the cases. So if you are talking about a simple pendulum, when we disturb it from its equilibrium position, bring it here and leave, it keeps on oscillating with its own frequency, which we call it as natural frequency, and they are natural oscillations. Now, these oscillations, because of the damping forces that are acting on them, they will gradually die out. The amplitude keeps on decreasing and then the body comes to rest. But if we want to sustain these oscillations, we are applying an external force, which we call as applied external periodic force. So now, when the frequency of the applied force equals the natural frequency, then we get resonance, and the effect of resonance is maximum amplitude. Now this object will vibrate with larger amplitude. That is the effect of resonance. What is happening here? The external frequency and the natural frequency will match with each other. Next, define intensity of a wave. What is intensity? It is nothing but the ratio of energy per second passing normally through a given area. So if you are taking an unit area, what is the ratio of the energy that is passing through it per second gives us the intensity of the wave. Now recall angular velocity. What is angular velocity? For a point describing a circle at uniform speed, the angular velocity omega is equal to the angle theta swept out by the radius in time t. So let us consider this movement of a point which is describing a circle at uniform speed. So what we do is we will consider, if this is the center, this is the point P, which is moving along the circle. Now, how do we write angular velocity? Omega is equal to theta upon t. Now, if this is the radius vector, after a time t, the radius vector has swept an angle theta in time t. So, I can calculate the angular velocity omega is equal to theta upon t. What is theta? It is the angle swept out by the radius vector in that particular time t. Now, using this, we are also going to define for the entire oscillation. If you see, if the particle moves one complete circle, then it moves through an angle of 2 pi. And the time, we call it as the time period. So, we will also write it as omega is equal to 2 pi upon t. Now, explain the meaning of free oscillations. What are free oscillations? Free oscillations occur when an oscillating system is displaced and released. Means we are not applying any force, external force on the object. We are just displacing the system, be it a spring or a pendulum or a swing, whatever it is. We are just displacing it from the mean position and leaving, and then the system will oscillate with its own natural frequency, and then we call them as free oscillations. The frequency of free oscillations is known as natural frequency. Means the system will now oscillate with its own frequency called the natural frequency. Next, define period. Period T of a point describing a circle. So it is the time taken for one complete circle. We have already discussed. So if I am considering a particle moving along the circumference of the circle, this is the point which is moving along the circumference of a circle. Now, what is the time period? The time taken for one complete oscillation. We call it as T, capital T. It is always denoted by capital T. Time period always is the time taken for one complete oscillation. Describe a mechanical wave. What is a mechanical wave? So, it is a type of wave that involves matter. Example, ocean waves. Ocean waves are mechanical waves. And also the waves you see in a string. When you just pluck a string and leave it, you see the waves in a string. All these are examples of mechanical waves. So what is happening in these waves? The matter may move in its place only about its mean position. It is the same in all types of motion. So there is no net movement of matter. Only the energy is propagated forward. So when we are talking about waves, the particles of the medium vibrate about their mean position and the energy is propagated in the forward direction. The matter itself is not moving away from its position. It is only vibrating about the mean position, but the energy is transferred. Define wave motion. So how do we define wave motion? It is the transfer of energy and momentum from one point of the medium to the other without actual transport of matter. So if I am talking about a wave which is moving from here to here, now all the particles of the medium, they will only vibrate about the mean position. They will not come out from their position. They will only vibrate about the mean position. But what happens? The energy is transferred from this position to this position when the wave is moving forward. So it is the transfer of energy and momentum. Momentum is nothing but mass multiplied by velocity without the actual transport of matter. Matter is not being transported, only the energy is being transferred. Now, what are the three properties that a medium should possess for a wave to propagate? If a wave has to pass through a medium, so what should be the properties of that medium? So, the medium should have elasticity, it should have inertia to store the energy, and a little frictional force to avoid dissipation of energy. So, three things we want. One is elasticity. Because when it is elastic, it will try to come back to its original position. Then inertia. Inertia is the property of the object by which it cannot change its state of rest or position by itself. Then only it can store energy. And also it needs a little frictional force to avoid dissipation of energy or loss of energy. Now define transverse wave. What is a transverse wave? A very important definition when it comes to waves. The particles of the medium vibrate in a direction perpendicular to the direction of propagation of the wave. So this is the key word here. When we are talking about a wave, we have seen that the particles only vibrate about the mean position. They are not being displaced from their position. Only the energy is being transferred. Now, depending upon the direction of vibration of the particles, we are going to classify the waves. So, the first one is the transverse wave. So, in a transverse wave, the particles vibrate perpendicular to the direction of propagation of the wave. And then in a transverse wave, we have a series of crests and troughs. So the upward maximum displacement, we call it as crest, and the maximum downward displacement, we call it as trough. Now, the transverse motion occurs only through a medium which has got rigidity modulus or shape conservation. Wherever the shape is being conserved, there will not be any change in shape of that object due to the motion of the wave. Then we call it as transverse wave. So, for example, we are taking the string waves. So, when a wave passes through the string, the shape of the string does not change. It is conserved. So, rigidity modulus is nothing but shearing stress upon shearing strain, which is related to the shape of the object. So, let us see the simulation, how the particles vibrate here. Now, if I am taking, this is the string, the thin line which you see is the string, and all these balls are the particles. So, how are the particles vibrating? They are just vibrating about the mean position, up and down, up and down. And how is the wave propagating? Like that. So, what is the direction of vibration? It is perpendicular to the direction of propagation of the wave. So, we call it as transverse wave. So, if this is the direction of propagation of the wave and this is the direction of vibration, then we call it as. Now, at any instant, you just take a snapshot of it. What you see here is, you will see that a wave is formed like this. So, this upward maximum displacement, we call it as crest, and the downward maximum displacement, we call it as trough. Now, define longitudinal wave. So, what is a longitudinal wave? Again, depending upon the direction of vibration of the particle. So, if the particles vibrate parallel to the direction of propagation of the wave, we call it as longitudinal wave. So, in transverse, we have seen that the particles vibrate perpendicular. But here, the particles vibrate parallel. Let us see how they vibrate. Now, if you see a string, the same string you consider, depending upon the vibration of the particles. So, how are the particles vibrating now? About the mean position, to and fro. If this is the direction of propagation of the wave, so the vibration is parallel to the direction of propagation of the wave. So, then you will call them as longitudinal wave. So, longitudinal wave requires a medium with only elasticity of volume, that is the bulk modulus for its propagation. So, in this type of motion, the waves travel in the medium in the form of compression or rarefaction. Compression means where the particles come closer together. Rarefaction means where they are apart. Now, if you see the motion here, when the particles vibrate, at some positions they may come closer together. When they are vibrating, some positions they may come closer and some positions they may go apart. So, where they are coming closer together, like in this position, they are coming closer. In some positions they are apart. So, positions where they are close, we call it as compression, and where they are apart, we call it as rarefaction. So, in a longitudinal wave, we will have a series of compressions and rarefactions. Next, state the principle of superposition of waves. What is superposition of waves? So, superposition principle states that when two or more waves overlap in space, if you are having at least two waves, it can be more than two also, but when they overlap, what happens? The resultant disturbance at that point will be equal to the algebraic sum of the individual disturbances. So, let us see with the understand it with the help of this diagram. So, we are talking about a first wave whose displacement is y1. And there is another wave whose displacement is denoted by y2. And if these two waves arrive at a point simultaneously, or they overlap with each other. So, what happens? You see here, there is an overlap and this is the resultant wave. So, how do you calculate the resultant? It is the algebraic sum of the displacements due to the two waves. Y is equal to y1 plus y2. y1 due to the first wave, y2 due to the second wave. So the resultant is y. So y is given by y1 plus y2. Now define stationary wave. What is a stationary wave? Standing wave, also called as stationary waves. Sometimes we call these stationary waves as standing waves. It is a combination of two waves moving in opposite directions, having same amplitude and frequency. So what we have here is two waves we need. They have to travel in opposite directions and they superimpose on each other. They should have the same amplitude. Amplitude here represents the maximum displacement. Frequency here is the number of vibrations per second. Both the waves should have the same frequency and the same amplitude. Now let us understand it with this example. Now first I consider the blue wave. So the blue wave is moving like this. It is moving in this direction. Now when it comes here, it may come back or reflect back, or I consider another wave. You consider, let this be another wave, which is coming in this direction. So the second wave coming in the opposite. So they are coming in opposite directions. Two are opposite. And if you see, the amplitude of the first wave and the amplitude of the second wave both are the same. And the frequency means the number of vibrations per second are also same. Then what is happening? You have a stationary wave. So this we call it as a stationary wave. Define velocity of a wave. So how do you define the velocity of a wave? It is the distance traveled in 1 second. So the basic definition we have for velocity as distance upon time. So when we talk about the velocity of a wave, it is the distance traveled by the wave divided by the time taken. So that gives us the velocity of the wave. Now define velocity in terms of wavelength. How do you write the velocity in terms of wavelength? So if the distance traveled is equal to wavelength lambda, then the time taken to cover this distance will be the time period t. So let me draw the waveform. This is one complete wave. So the distance traveled by the wave in one complete cycle, we call it as lambda, the wavelength. So what is the distance traveled here? The distance traveled here is the wavelength lambda. And what is the time taken for one complete oscillation? We write it as t. T is the time period. That is the time taken for one complete oscillation. So if we go back to our basic definition, velocity is equal to distance traveled upon time. So what is the distance traveled here? It is lambda. So lambda. What is the time taken? It is the time period t for one complete cycle. So we will write it as lambda by t. So we get the formula V is equal to lambda by t. So we can express the velocity in terms of wavelength lambda. Now, how is a progressive wave different from a stationary wave? We have already seen a stationary wave. A stationary wave is a standing wave, okay, which is formed due to superposition of two waves that are traveling in opposite direction but having the same amplitude and frequency. Now, what is a progressive wave? A wave that moves forward into the medium and never comes back. That is what we call a progressive wave. So, how are they different? In a standing wave, the motion of the particles is non-transferrable. But in a progressive wave, the motion is easily transferred to the particles in the forward direction. That is how the wave progresses forward. And in stationary waves, the energy is confined to a certain region, while in progressive wave, there is propagation of energy. Two main differences between a progressive wave and a stationary wave. So, in a progressive wave, there is no transfer of the motion of the particles. and therefore in a stationary wave, the energy is confined to a limited region, whereas in case of a progressive wave, the energy is propagating forward or transferred forward. Then define nodes in stationary waves. What are nodes? So we have already discussed about stationary waves. So we know what a stationary wave is. Two waves traveling in opposite direction having the same amplitude and frequency. Now, what are nodes? It is a point along a standing wave where there is minimum amplitude. So when we are talking about these two waves having the same amplitude, but they are moving in opposite direction. So there are some points where the amplitude is minimum. You see these points where the amplitude is minimum, because in the first case, if at this point it is plus A and here it is minus A. So plus A and minus A will get cancelled and the resultant will be 0. So there is minimum amplitude. So wherever there is minimum amplitude, you will call them as nodes. So nodes are points in a stationary wave with minimum displacement or minimum amplitude. Now define antinodes. So once we know nodes, we can easily define antinodes. So they are the points with maximum displacement. So wherever the displacement is maximum, we are calling them as antinodes. So in each vibrational cycle, what we are talking about, if I am talking about this cycle, one complete cycle, there are points which are opposite of nodes. Why we call them as opposite of nodes? Because in case of nodes, the displacement is minimum, but in case of antinodes, the displacement is maximum. So here you see these positions, the displacement is maximum. So we call them as antinodes. So in nodes, it is minimum, and in antinodes, it is maximum. That is why we call them as antinodes. Node means minimum, anti of node is maximum displacement. Now, what is restoring force in damped oscillation? So, when we have talked about damped oscillations, we were talking about the restoring force. So, what is the force that tries to bring it back to its original position? And that force is proportional to the displacement, but always directed towards the mean position, that is opposite in direction to the displacement. So we always denote it by minus mu y. So I write it as F, the restoring force, is equal to minus mu y. In some notations, we also write it as minus kx. If we are considering x as the displacement and k as the spring constant, we write it as F is equal to minus kx. So what is the frictional force in damped oscillators? A damped system which is subjected to a frictional force which is proportional to the velocity but opposite in direction, we call it as damped frictional force in damped oscillators, and it is denoted by minus gamma v. When we are writing the frictional force or the damping force, Fd, it is denoted by minus gamma v. V here is the velocity which is given by dy by dt, rate of change of displacement. So we write the damping force as minus gamma into dy by dt. So this force, the damping force, is due to the frictional force. So we write it as minus gamma dy by dt. Now what is the external periodic force in a forced oscillation? So whenever we are talking about forced oscillation, there should be some external periodic force. So what is that external periodic force? So the force that is exerted on the oscillator, which is represented by F sine pt. This is what we call it as the external periodic force. So where F is the maximum value of the force and P by 2 pi is the frequency. Because we are talking it is periodic, so what is its frequency? It is given by P by 2 pi. Now what is oscillation? So we have already discussed in detail. So it is defined as the process of repeating variations of any quantity or measure about the equilibrium position with respect to time. And oscillation can also be defined as the periodic variation of matter between two values or about its central value or the mean position, we call it. And then the term vibration, we are using it to describe the mechanical oscillations. So whenever we have discussed mechanical oscillations, the particles of the medium vibrate about their mean position. So we call them as oscillations. Now, when can an oscillation remain undamped? So when is the damping, underdamping? So an oscillation remains undamped or underdamped when the restoring force equals the restraining force. So restoring force is the force which tries to bring it back to the normal position, and the restoring force is always an opposing force. So when these two are becoming equal, then what happens? It is going underdamped. So here what we are defining, an oscillation remains underdamped when a restoring force equals the restraining force is induced and the system oscillates with the same energy. There is no dissipation of energy because the restoring force and the restraining force are equal. So we call it as undamped oscillation. Then define damping. Damping is the process of restraining or controlling the oscillatory motion. So how are we restraining? Due to the opposing forces, the motion of the object or the system is restrained. Then we are calling them as damped oscillations. So in this case, what happens? There is dissipation of energy. So wherever there is damping, there is dissipation of energy, and we also call them as controlled oscillatory motion. Next, define compression and rarefaction in a longitudinal wave. So when we have discussed a longitudinal wave, we said there are a series of compressions and rarefactions. So what is a compression? A compression is a region in a longitudinal wave where the particles are closer together. When they are closer together, we call it as compression. And rarefaction is a region where the particles are farther apart. So let us see it with the help of this diagram. So you can see the simulation here. The particles are vibrating. They vibrate parallel to the direction of propagation of the wave. But when they are vibrating, you see at certain regions. So at certain regions, what is happening? The particles are close, and certain regions, the particles are apart. So when they are close, we are calling it as compression. And when they are apart, we are calling it as rarefaction. So with this, we will end our discussion here. Thank you, and see you again in the next lecture.
Like, share and subscribe. Hit the bell icon for more updates.